We physicists have waited 100 years since 1916 for this photograph.
In the vastness of space, humanity's enduring fascination with the universe has led to the exploration of distant galaxies and the phenomena of celestial bodies. Among these wonders, black holes have remained mysterious due to their distortion of physics, warping space and time into an impenetrable abyss. In a historic achievement, scientists have, for the first time, delved into the inner workings of a black hole.
The Earth goes around the Sun. But what does the Sun go around?
However, this breakthrough prompts us to question whether the reality inside these cosmic objects matches the ominous portrayals often seen in popular culture. So, join us as we accompany researchers on their unprecedented journey to the heart of a black hole, where they aim to unveil the concealed mysteries therein, the cosmic conundrum that challenges physics. While many of us have a basic grasp of what black holes are, there remain intriguing gaps in our understanding. Black holes possess an inherent sense of mystery, evoking a profound fascination due to their captivating nature. Within this enigmatic realm, time behaves in a perplexing manner, challenging even the most brilliant minds as they grapple with its bewildering characteristics. This prompts the fundamental question: what exactly defines a black hole, and what bestows upon this seemingly inconspicuous void its profound significance and immense influence? The concise answer lies in the pervasive force of gravity, and it is this gravitational attraction that endows black holes with their profound impact. However, a more intricate and engaging explanation delves deeper into this phenomenon. Black holes originate from the remnants of deceased stars, referred to as stellar cores, undergoing cataclysmic collisions. When the accumulated mass surpasses approximately 3 times that of the Sun, gravity asserts its dominance, overwhelming all other forces. This overpowering gravitational force compels the remnant to collapse inward, resulting in the formation of a black hole. These enigmatic celestial entities are distinguished by their extraordinary density, possessing such immense mass that their gravitational pull is so overpowering that even light cannot escape their grasp. The prevailing consensus among astronomers is that the majority of spiral and elliptical galaxies house black holes at their central cores. Black holes can be categorized into 3 distinct groups for our comprehension. The initial group encompasses stellar mass black holes, which are the smallest in size, typically ranging from 1 to 100 times the mass of the Sun. These black holes result from the gravitational collapse of massive stars, frequently accompanied by a supernova or a stellar explosion. Conversely, at the other end of the scale, supermassive black holes reign supreme, possessing masses that extend into the millions, if not billions, of times that of our Sun. These colossal entities are believed to have achieved their tremendous proportions through the amalgamation of other black holes and the accretion of surrounding stars. Intermediate mass black holes represent the third category, occupying a middle ground between their stellar and supermassive counterparts. Although relatively scarce in number, with only a few confirmed instances, these black holes are estimated to possess masses ranging from 100 to 100,000 times that of the Sun. Michio Kaku postulates that these intermediate mass black holes serve as the foundational elements in the eventual development of supermassive black holes through a process of mergers and accretion. Beyond their role in deciphering the seemingly perplexing movements of specific stars and their contributions to our comprehension of galactic structures, black holes introduce an uncharted frontier in physics for the scientific community. Black holes and the battle of theories. In line with Albert Einstein's pioneering theory of general relativity, we explore the captivating occurrence where matter exerts its influence on the fabric of space-time, ultimately giving rise to the force recognized as gravity. Black holes, these mysterious cosmic entities, manifest as dense celestial agglomerations of matter, possessing an extraordinary gravitational attraction. Nevertheless, the true wonder lies in the examination of a black hole's singularity, where the forces involved reach astonishing magnitudes, leaving the scientific community in deep reflection. Einstein's general theory of relativity suggests that as matter succumbs to the gravitational pull of a black hole, Its informational essence faces complete obliteration. In contrast, the principles of quantum mechanics strongly contest this idea, asserting that such annihilation cannot occur. Interestingly, black holes emerge as a significant crucible for astrophysicists and mathematicians, providing a fertile ground for the reconciliation of these two divergent theories. A prevalent misconception exists concerning black holes, often associated with the mistaken image of a literal hole in space. However, this notion is far from accurate. Black holes can be more aptly likened to cosmic supermagnets, distinguished by their extraordinary gravitational forces, possessing an unparalleled ability to attract matter. In essence, gravity serves as the underlying force responsible for keeping us anchored to Earth, preventing our untethered ascent into the vastness of space when we leap skyward. It is crucial to understand that Earth's gravity consistently draws objects toward its center, ceasing to do so only once they reach its surface. Conversely, black holes wield gravitational forces of staggering strength, far surpassing Earth's relatively feeble hold. What distinguishes them is the stark absence of a discernible surface to halt one's inexorable descent, thus creating the impression of falling into an inescapable chasm, hence the term black hole. The genesis of a black hole traces back to the dramatic collapse of a massive star, resulting in the formation of an entity of remarkable density. Within this enigmatic cosmic entity, an entire star's worth of matter becomes compressed into a minuscule volume. This accumulation of mass inherently leads to an increasing gravitational influence. As the saying goes, mass begets gravity. In simpler terms, the more mass an object possesses, the greater its gravitational force. This principle underscores the reciprocal gravitational attraction between Earth and its inhabitants. Nonetheless, it is crucial to note that an individual's gravitational pull is intrinsically linked to their mass or weight. In stark contrast to a celestial body like Earth, the human body exerts a significantly weaker gravitational influence. This explains the peculiar phenomenon where astronauts on the Moon appear to weigh less. This observation arises from the Moon's reduced mass compared to Earth, resulting in a diminished gravitational pull on its surface, thereby creating a perception of reduced weight for objects and individuals present there. The concept of black hole compressibility. The concept of black hole compressibility presents an intriguing and perplexing notion. It is quite astonishing that a star with a mass equivalent to that of our Sun can undergo a collapse, resulting in the formation of a black hole occupying a volume comparable to that of a modest city. The extreme density inherent in this transformation is a formidable challenge for the human intellect. To put this into perspective, consider that the Sun's diameter spans approximately 1,400,000 kilometers, whereas a small city typically extends merely 10 kilometers in length. This substantial reduction in volume underscores the remarkable transformation of an entire star. This underscores the notion that referring to black holes as holes is accurate only when considering their profound gravitational impact on their surroundings, rather than reflecting their intrinsic nature. As we delve deeper into this subject, it becomes abundantly clear that black holes are exceedingly intricate celestial entities. So, if black holes are not mere voids, what precisely are they? From a technical standpoint, black holes can be characterized as spherical entities, defined by two principal components: the singularity at their core and the theoretical boundary commonly known as the event horizon. The singularity serves as a point of virtually infinite density devoid of any volume. It exerts an irresistible gravitational force, thereby constituting the defining essence of black holes and the fundamental driver behind their distinctive characteristics. The singularity located at the heart of a black hole exhibits remarkable smallness and density. To illustrate this concept, consider standing at the North Pole of our planet. Gravity in the northern hemisphere is stronger than in the southern hemisphere, owing to the inverse relationship between gravity and distance. This means that we do not experience Earth's gravitational pull uniformly at all times. Regions of Earth situated closer to us exert a more potent gravitational force, while those farther away exert a weaker pull. However, if we were to compress all of Earth's mass into a smaller volume, the gravitational force would intensify. Importantly, the total mass remains constant. What changes is the density. Elevated density translates into a more concentrated mass, and consequently, a stronger gravitational pull. This comprehension of black holes and gravity unveils their captivating nature, challenging our understanding of space, time, and the principles governing the physical universe. Black holes continue to captivate the imagination and remain a subject of extensive exploration and research in this captivating field. Michio Kaku. We finally found what's inside a black hole. Renowned theoretical physicist Michio Kaku has dedicated decades to the pursuit of a comprehensive theory, commonly known as the theory of everything. Among the numerous conjectures in this realm, one has exhibited notable promise: superstring theory. Superstring theory represents a synthesis of gravity and radiation theory, postulating that subatomic particles are essentially minute vibrating strings. It envisions the cosmos as a symphony of these strings, analogous to distinct musical notes corresponding to varying vibrations of a violin string. Similarly, diverse particles in nature align with distinct vibrations of a superstring. What distinguishes superstring theory is its capacity to warp the spatial fabric, engendering phenomena like black holes, wormholes, and other intriguing solutions derived from Einstein's equations, as these strings traverse through time. This theoretical framework not only harmonizes Einstein's gravitational theory with quantum theory, but also elucidates numerous enigmatic natural occurrences. Yet, a facet of this theory complicates its apparent simplicity. It necessitates the existence of 10 dimensions within space-time. This stark contrast to our daily perception of 3 spatial dimensions and 1 temporal dimension seems perplexing. To fathom these additional dimensions, we can draw an analogy with a 2-dimensional pond inhabited by fish, which solely grasp length and width. In their reality, height is inconceivable. However, when raindrops disturb the pond's surface, the fish perceive ripples, indirectly acknowledging the existence of a 3rd dimension. Analogously, physicists posit that we cannot directly perceive these extra dimensions of space-time. Instead, we can detect their influence on our familiar world. Specifically, the vibrational motions of strings within superstring theory generate energy waves traversing these hidden dimensions. These waves manifest as particles with unique attributes such as mass and charge. In this manner, superstring theory offers the potential to elucidate all observed particles and forces, encompassing the enigmatic realm of gravity. However, a significant challenge arises from the minuscule scale of these extra dimensions required by superstring theory. Regrettably, direct exploration remains elusive, as our laboratories can only precisely measure the 4 dimensions we commonly encounter: length, width, depth, and time. Crossing the point of no return. In cinematic portrayals and visual representations, the event horizon is commonly rendered as a shadowy circular boundary in the expanse of space, enveloping our conventional notion of a black hole. This boundary marks a critical threshold, often referred to as the point of no return, encircling the central core. Once traversed, anything that ventures past the event horizon experiences an immediate and inexorable gravitational pull towards the core with no conceivable means of escape. Notwithstanding its appearance as a tangible perimeter, it is imperative to grasp that the event horizon lacks physical substance and harbors no contents within. It is pivotal to recognize that black holes do not conform to traditional objecthood, as they predominantly comprise vast voids. The singularity, nestled at the heart of a black hole, contains all the amassed matter, while the space encompassing it remains, for the most part, an emptiness devoid of substance, presenting an illusion of profound darkness. Any substance or energy that ventures into the black hole rapidly gravitates towards the central singularity, merging with it in a fraction of a moment. The gravitational force exerted by black holes is exceptionally formidable. Its intensity is so overwhelming that not even light can evade it, rendering black holes impervious to direct observation. Consequently, in lieu of conventional telescopic instruments, scientists must rely upon colossal radio telescopes and gravitational wave detectors to indirectly detect and investigate these enigmatic cosmic phenomena. the laser interferometer breakthrough. In the year 1915, Albert Einstein introduced a revolutionary concept that pertains to the influence of objects in motion within the spatial domain on the very fabric of spacetime. This profound insight essentially converged the previously distinct domains of space and time. This phenomenon can be likened to the manner in which disturbances propagate across the surface of a tranquil pond. Fast forward to the year 2025, a full century later, when a momentous breakthrough was achieved by scientists at the Laser Interferometer Gravitational Wave Observatory. For the very first time in history, they directly observed gravitational waves. This remarkable feat was the consequence of the collision between two black holes that transpired 1.3 billion years ago. The presence of black holes can be discerned through their profound impact on the surrounding celestial environment, notably their capacity to attract and superheat gas, dust, and stars. As these materials are drawn toward the black hole, they emit detectable radiation manifesting as thermal signatures. In April 2019, the Event Horizon Telescope, an assemblage of 8 terrestrial radio telescopes meticulously designed for capturing imagery of black holes, achieved a monumental milestone. They successfully imaged a black hole and its enshrouding shadow for the very first time. The target of this groundbreaking image was the black hole situated within the Messier 87 galaxy, an integral part of the Virgo galaxy cluster. The captured image portrays a luminous ring encircling the black hole, which is situated approximately 55 million light-years distant from Earth and possesses a mass 6.5 billion times greater than that of our Sun. This radiant ring, known as the halo, signifies the intense thermal emissions produced by the swirling hot gas in close proximity to the event horizon, the outermost periphery of the black hole before it succumbs to its inexorable gravitational pull. Theoretical scenarios of black hole travel. When pondering the consequences of an individual falling into a black hole, it becomes evident that such an occurrence would be highly unfavorable. Regardless of encountering various types of black holes, the prognosis remains quite grim. For the sake of hypothesis, should an individual impulsively venture into a stellar mass black hole before any intervention could take place, their physical form would undergo a distressing phenomenon termed spaghettification. Despite the somewhat whimsical nomenclature, the reality is far from humorous. The colossal gravitational influence of a black hole would compress the person from head to toe while simultaneously stretching their body, resulting in a configuration akin to that of spaghetti. Opting for a supermassive black hole does offer a comparatively less dreadful outcome. Let us consider, perhaps for the pursuit of scientific inquiry or a momentous leap for humanity, that an individual chooses to plunge into Sagittarius A, a supermassive black hole residing at the heart of the Milky Way. This celestial entity, discovered by astronomers Bruce Balick and Robert L. Brown in 1974 and subsequently christened in 1982, boasts an estimated diameter of approximately 44 million kilometers and a mass equivalent to 4.31 million times that of our Sun. The journey into Sagittarius A star commences as soon as the person crosses the event horizon, marking the point of no return. While within, one could still perceive the external surroundings, but any observer from beyond would be incapable of discerning them. Any emitted light from within would be ensnared and redirected inward, rendering the individual invisible to external observers. The reassuring news is that, despite the considerably greater gravitational force within such colossal black holes, the stretching tidal effect is relatively weaker, diminishing the likelihood of being elongated into spaghetti-like strands. It is imperative to underscore that these scenarios remain purely theoretical due to the extreme characteristics of black holes, which render direct observation and exploration unattainable. Nevertheless, the investigation of black holes continuously captivates scientists, further enriching our comprehension of the intricate mechanisms governing our universe. Escaping from a black hole is an exceedingly formidable undertaking, if not entirely implausible. However, a glimmer of optimism emerges in the form of the white hole theory. In straightforward terms, while black holes draw matter inward, white holes eject it, though their precise nature remains mysterious. Fortunately, there exist conduits known as wormholes that link black holes and white holes. Wormholes propose the potential for travel from a black hole to a white hole, though this journey would span billions of years. It is vital to bear in mind that this concept is still in the realm of research and refinement. According to Kaku, we should refrain from raising undue expectations or taking uncalculated risks solely predicated on this theory. While the notion of white holes and wormholes is intriguing and presents prospects for interstellar travel, it remains speculative and necessitates further scientific exploration and development. Resisting the gravitational abyss. Let's explore the intriguing territory within a black hole and consider the outcomes of being trapped by its gravitational force. In this enclosure, one can significantly contribute to human knowledge by conducting experiments. These efforts might challenge the conventional idea that matter undergoes an endless compression into a single point deep within a black hole. Instead, a plausible alternative arises in the form of a Planck star, a theoretical concept proposed by loop quantum gravity. It's important to note that loop quantum gravity itself falls under speculative scientific theories, aiming to establish a quantum framework for comprehending gravity's fundamental force. In this framework, space-time becomes quantized, consisting of discrete units or chunks. These units, however, operate at a very small scale, which makes our large-scale movements appear continuous. The theoretical granularity of space-time offers two significant advantages. Firstly, it provides a coherent explanation for gravity within the quantum mechanical framework. Secondly, it prevents the formation of gravitational singularities at the core of black holes. As matter succumbs to the relentless gravitational force and compresses within a collapsing star, it encounters resistance due to the discrete nature of space-time. This resistance limits matter's compression beyond the Planck length, roughly 1.68 times 10 to the power of minus 35 meters. Consequently, everything that descends into a black hole is condensed into a compact entity, though not infinitesimally small. This resistance to further compression ultimately reverses the collapse, using a gentler term than explosion. Consequently, black holes appear as temporary entities, destined for a finite existence. However, due to the extreme time dilation effects near black holes, their end unfolds over billions or even trillions of years when viewed from the external universe's perspective. Gravis stars and the singularity problem. The notion of a Gravis star represents a fresh initiative aimed at addressing the perplexing singularity issue without relying on unverified quantum gravity theories. Despite its seemingly ad hoc label, astronomy occasionally employs such naming conventions. However, it is crucial to distinguish the fundamental difference between a black hole and a Gravis star. The latter is distinguished by the presence of dark energy instead of a singularity. Dark energy is a pervasive cosmic entity that permeates both space and time, causing an outward expansion effect. While this might seem like science fiction, it is an established reality. At present, dark energy actively propels the accelerated expansion of our universe on a cosmic scale. Regarding Gravis stars, when matter falls into them, it encounters a formidable obstacle in the form of the interior's dense dark energy, preventing penetration beyond the surface. This stands in sharp contrast to black holes, which possess an event horizon, a critical boundary beyond which nothing, not even light, can escape. Recent observations by gravitational wave detectors like LIGO and Virgo during black hole mergers have cast doubt on the existence of Gravis stars. This uncertainty arises from the distinctive signals generated by merging Gravis stars, which differ from those produced by merging black holes. These detectors continue to accumulate new data, further fueling skepticism about the feasibility of Gravis stars. It is important to clarify that Gravis stars are not explicitly prohibited within the framework of our universe, but their theoretical basis remains precarious, subject to ongoing scrutiny and evaluation. Now it's time for today's subscriber pick. A previously unknown black hole was discovered as it tore apart and devoured a star that ventured too close. This event occurred in a small galaxy located 1 million light-years away, known as a tidal disruption event, TDE. The TDE became visible when it emitted an intense burst of radiation, briefly outshining all other stars in the galaxy. This discovery provides a chance for scientists to deepen their understanding of the relationship between galaxies and black holes. It also offers a new intermediate black hole for examination, aiding in the study of their masses. This groundbreaking finding has generated significant interest and promises to advance our cosmic knowledge. Let us know what you think about what we just showed you. Exploring ring singularities and wormholes. Planck stars and Gravis stars, though intriguing in name, are not the sole contenders in the exploration of the mysterious phenomenon of singularities. Researchers have proposed an alternative perspective, based on a more advanced understanding of black holes, one that departs from the concept of a single point of infinite density. This idea stems from our comprehension of non-rotating, uncharged black holes, which are admittedly less captivating. Genuine black holes, however, exhibit fascinating behaviors, especially when they possess angular momentum. The rotation of a spinning black hole stretches the singularity into a ring-like structure, as outlined by Einstein's general theory of relativity. Transitioning through this ring singularity leads to the possibility of a wormhole and, subsequently, emerging through a white hole into an entirely new and thrilling cosmic realm. A challenge arises due to the inherent instability within the interiors of rotating black holes, a consequence of their rapid rotation. This instability generates substantial centrifugal forces, similar to anti-gravity, which push rather than pull. Consequently, an inner horizon forms within the black hole. Within this region, radiation from outside the black hole is compelled by intense gravitational forces to move inward toward the singularity. Paradoxically, the radiation experiences anti-gravity effects near the ring singularity, driven by the centrifugal forces. The inner horizon serves as a crucial boundary. Any interaction with it would expose an individual to an intense burst of infinitely energetic radiation, summarizing the universe's history in an instant. Rotating black holes. The inception of an inner horizon signifies the initial phase in the formation of black holes. However, the existence of rotating black holes in our universe presents a substantial challenge to the accuracy of our mathematical formulations, hinting at the presence of unique phenomena. Fortunately, the introduction of a groundbreaking concept known as gravitational waves has afforded us our first glimpse into the mysterious interiors of black holes. This recent research effort holds the potential to significantly enhance our understanding of the catastrophic events that occur when these cosmic entities collide, a phenomenon of utmost rarity and cosmic drama. In 2015, scientists achieved a historic milestone by detecting gravitational waves for the first time. This accomplishment was realized through the use of complex and monumental instruments designed to monitor disturbances in the fabric of space-time resulting from the collision of black holes. The repercussions of this collision ripple throughout the universe, much like the waves generated when shaking a sealed container and deciphering its contents by analyzing the resulting sounds. In the case of gravitational waves, the perturbations arise from the collision of two black holes and the information gleaned from studying these gravitational waves. Consequently, scientists have employed these measurements to refine their models of celestial events, enabling a deeper exploration of the internal dynamics at play and allowing for scrutiny of the validity of Einstein's theory of general relativity in extreme cosmic environments. These advancements position us to embark on a journey towards unraveling the mysteries concealed within the core of black holes. A quantum leap in scientific predictions. Until recently, scientific models primarily relied on linear interactions as the foundational framework for their predictive capabilities. Although these models have demonstrated their effectiveness, they inherently possess certain limitations, as they fail to encompass various forms of behaviors that can manifest within intricate systems. Nevertheless, ongoing research into nonlinear interactions offers a compelling opportunity to enhance these models significantly, with the potential to improve their precision by as much as 10%. This advancement carries substantial promise, particularly in the context of detecting colliding black holes, as it has the potential to empower scientists with greater accuracy and confidence when identifying and investigating such occurrences in the future. The progress in comprehending non-linear interactions signifies a substantial stride forward in our relentless pursuit to decipher the enigmas of the universe. By integrating these newfound insights into gravitational wave detection methodologies, we draw ourselves nearer to the subsequent phase of exploration. This advancement harbors the capacity to enrich our understanding of gravity itself and the breathtaking phenomena unfolding within the vast expanse of the cosmos. The hidden secrets of holographic duality. The Laser Interferometer Gravitational Wave Observatory, renowned for its groundbreaking gravitational wave discoveries, has been offline since 2020 due to the pandemic. However, upcoming system activations offer hope for enhanced black hole detection and study. A recent University of Michigan study, led by Enrico Rinaldi, delves into the intriguing notion that black holes may be analogous to holograms. Notably, this comparison doesn't depict black holes as science fiction-like projections, but instead employs holography to investigate the relationship between a black hole's interior and exterior. This research builds on the principle of holographic duality, which mathematically equates gravity and particle theories. Gravity theory deals with the third dimension, while particle theory accounts for the second. Both are vital in comprehending black hole operations. The study's goal is to uncover the implications of holographic duality for black holes, aiming to unveil their concealed mysteries. The key to intermediate black hole mass determination. The TDE flare, which was initially identified in the year 2020, was first observed by astronomers using the Young supernova experiment. This astronomical survey was specifically designed to detect transient cosmic phenomena, such as supernova explosions. The early detection of the black hole commencing the ingestion of the nearby star played a pivotal role in facilitating an international collaborative effort. This initiative was led by scientists hailing from the University of California, Santa Cruz, and the Niels Bohr Institute. Notably, astronomer Charlotte Angus was among the key contributors to this endeavor. As a result of this collective endeavor, the research team successfully determined the mass of the black hole with a precision that places it within the range of 100,000 to 1 million times the mass of our Sun. It is worth highlighting that prior to this discovery, tidal disruption events had primarily been utilized to estimate the masses of massive supermassive black holes. However, this groundbreaking achievement marks the first instance in which TDEs have proven effective in ascertaining the masses of intermediate black holes, particularly those of smaller to mid-sized proportions. Consequently, the initial observation of this remarkably rapid flare assumes a crucial role as a benchmark for future measurements pertaining to mid-sized black hole masses. By capturing the mid-sized black hole in the act of engulfing a neighboring star, researchers unveiled information that would otherwise have remained concealed. The flares emanating from these black holes furnish vital insights into the realm of intermediate black holes, which may constitute the majority of black holes situated at the centers of galaxies. Scientists posit that supermassive black holes, significantly larger than our Sun, may have formed through the merger of smaller intermediate black holes. In the early universe, smaller galaxies harbored these intermediate black holes. When these galaxies amalgamated or were absorbed by larger galactic entities, their black holes coalesced, resulting in their growth. This cyclical process subsequently contributed to the formation of the immense, supermassive black holes that are now prevalent within most galaxies. A significant question that persists in astrophysical inquiry revolves around the presence of intermediate black holes in all small galaxies. The inherent challenge lies in the elusive nature of black holes, as they only become observable when actively accreting matter or perturbing stellar bodies due to their light-capturing characteristics. What aspect of the black hole phenomenon intrigued you the most? Let us know in the comments below.